Hello everyone, I am Federica Arrigoni from the University of Trento and I will speak about synchronization and cycle consistency, application to motion segmentation and localization. This is part of a tutorial on cycle consistency and synchronization in computer vision, developed in collaboration with Tolga Birdal and Leo Gibas from Stanford University and Qixing Huang from the University of Texas. This is the outline of my presentation, which is divided into parts. The first part is about synchronization and motion segmentation, whereas the second part is about cycle consistency and localization. I will start with an introduction to the synchronization problem, where I will briefly explain spectral methods and possible applications. Consider a network of nodes where each node is characterized by an unknown state, and pairs of nodes can measure the difference between their states. The goal is to infer the unknown states from the pairwise measures, as shown in the figure. Observe that the solution is not unique, for adding a constant to all the nodes does not change the differences. This example refers to time synchronization, from which the term synchronization originates, where the task is to synchronize clocks in a network, starting from pairwise offsets. This problem can be generalized considering a group instead of the set of real numbers. More abstractly, the goal of synchronization is to recover elements of a group, given a certain number of their mutual differences or ratios, depending on how the operation is called. The relation between unknowns and measures is called the consistency constraint. Observe that the solution is not unique, as it is defined up to a global product with any group element. Synchronization can be modeled as a graph, where nodes correspond to the unknowns and edges correspond to the measures, as shown in the figure. The problem is well posed only if this graph is connected. We are particularly interested in groups admitting a matrix representation. In this case, the unknown elements can be recovered via spectral decomposition. Let us collect all the measures in a big block matrix Z, and let us collect all the unknowns in a block matrix as X, as shown in the formulas. Using this notation and exploiting the consistency constraint, we get the boxed formula. Z times X is equal to N times X, where N is the number of nodes. This means that the columns of X are eigenvectors of Z with eigenvalue n. In order to fix the group ambiguity, the first element can be set to the identity. Moreover, the solution needs to be projected onto the group. Indeed, the spectral solution is an algebraic approach that does not enforce the geometric constraint of the specific group of interest. This derivation assumes full measures, but it can be easily extended to the case of missing data by using the adjacency matrix and the degree matrix of the graph. Moreover, it can also be made robust to outliers by using iteratively reweighted least squares. The spectral solution has been applied to several matrix groups in computer vision literature, as shown in the figure. One example is the set of rotations, also known as the special orthogonal group, which admits a matrix representation through orthogonal matrices with unit determinant. In this case, the projection is done via singular value decomposition. Synchronization of rotations is an essential task within structure from motion, that is, the problem of recovering camera motion and scene structure, starting from multiple images of a static scene. Another example is the set of rigid motions, which represent rotations followed by translations in the Euclidean space, as shown in the formula. Also in this case, the final projection is performed via singular value decomposition. Synchronization of rigid motions finds application in registration, where the task is to find the rigid transformations that bring multiple point clouds into alignment. The spectral solution has also been applied to permutation synchronization, which finds application in multi-view matching, as shown in the figure. A permutation matrix has exactly one non-zero entry in each row and column, and these non-zero entries are all equal to 1. In this case, the final projection step is a linear assignment problem. Another example is the set of homographies, which can be identified with matrices with unit determinant, that form the so-called special linear group. This group is related to the problem of aligning multiple images into a mosaic, as shown in the figure. In order to project the solution onto a valid element of the group, it is enough to divide by the dth root of the determinant, which works if d is odd. Now I will explain in detail another problem where the spectral solution can be used, that is motion segmentation. The task of motion segmentation is to classify points in multiple images based on the moving object they belong to, as shown in the figure. It is assumed that objects are moving rigidly and independently in tree space. Previous works on motion segmentation can be grouped into three main categories, namely trajectory clustering, segmentation with two-frame correspondences, and segmentation with unknown correspondences. This taxonomy reflects the different levels of prior assumptions made on input data, as shown in the figure. We consider here the middle category, where pairwise matches are assumed as input. This represents a good trade-off between making realistic assumptions and addressing a feasible task. We also assume that the number of motion is known and constant over frames. Now I will show that motion segmentation can be seen as a synchronization of binary matrices, that are matrices whose entries are either 0 or 1. Given a pair of images, we can define some binary matrices as shown in the figure. The partial segmentation of the pair ij is denoted by zij, and it is defined as follows. Entry hk is equal to 1 if point h in image I and point k in image j belong to the same motion, and it is equal to 0 otherwise. The total segmentation of image I is denoted by xi, and it is defined as follows. Entry hk is equal to 1 if point h in image I belongs to motion k, and it is equal to 0 otherwise. The partial segmentation reported in the middle of the figure is a local representation of segmentation, since it says which points into images belong to the same motion, but it does not say which motion it is. The total segmentation instead is a global representation of segmentation, since it says which points in a given image belong to each motion. Total segmentations represent our unknowns, whereas partial segmentations are considered known, as explained in the next slide. The link between total and partial segmentations is given by the consistency constraint, as shown in the formula. This suggests that motion segmentation can be solved in two steps. First, each partial segmentation is computed by fitting multiple fundamental matrices to corresponding points. Then, total segmentations are derived via synchronization using the spectral solution. Let us collect all the partials and total segmentations into block matrices Z and X, as shown in the formula. The consistency constraint can be rewritten in matrix form as Z is equal to X times X transpose, which implies that Z has rank D. Observe that the product of Xi transpose and Xi is a D times D diagonal matrix, such that the entry in position kk counts the number of points in image I that belong to motion k. Thus, X transpose X is a diagonal matrix such that the entry in position kk counts the number of points over all the images that belong to motion k. Using this observation and the consistency constraint, we get the equation reported in the bottom part of the slide. Z times X is equal to X times a diagonal matrix. In other words, the columns of X are the eigenvectors of Z, where D denotes the number of motions. If each motion contains a different number of points, then the eigenvalues are distinct. Observe that these are the leading eigenvalues and all other eigenvalues are 0, since Z has rank D. This suggests an heuristic procedure to solve motion segmentation. First, the top D eigenvectors of Z are computed. Then, they are projected onto a binary matrix using a greedy strategy based on maximums over rows. Indeed, we expect that for each row, the entry that reveals the membership to a specific motion is close to 1, and all other entries are close to 0. The spectral solution can be interpreted in terms of an optimization problem. Let us consider the following cost function, which counts the number of points equally labeled by the partial segmentations Zij and Xi transpose for each image pair. Observe that the columns of X are orthogonal since each point belongs to one motion only. In order to make the computation tractable, let us consider the spectral relaxation, where the optimization variable is treated as a real matrix instead of a binary matrix, and its columns are enforced to be orthonormal. In this way, we get a Rayleigh problem, whose solution is given by the leading eigenvectors of Z. Now I will explain a different approach to solve motion segmentation, that is, a local solution. As done by the spectral solution, motion segmentation is solved in two steps. First, segmentation of corresponding points is performed on each image pair in isolation, for instance by fitting multiple fundamental matrices. Then, the partial results derived in step 1 are combined in order to get a multi-frame segmentation. The difference between the spectral method and the local solution lies in the second step. The key observation is that all the two-frame segmentations involving a fixed image provide an estimate for the segmentation of that image. Observe that there is a permutation ambiguity in the labeling of motions, since each pair has been considered independently from the others. For instance, with reference to the figure, the star is given the yellow label in two pairs and the purple label in one pair. The permutation ambiguity can be solved via permutation synchronization, as explained in the next slide. At the end, for each point in each image, several putative labels are available, and the most frequent label is chosen. This handles noise in individual pairwise segmentations. Now I will explain how to fix the permutation ambiguity. Let us consider a graph representation of the problem. Each vertex corresponds to one pair of images. An edge is present between two vertices if and only if the associated pairs have one image in common. Vertices are associated with unknown permutations and edges are associated with known permutations, as shown in the figure. Observe that the size of permutation matrices is equal to the number of motions, which is known by assumption. For each edge, a permutation matrix is computed by solving a linear assignment problem. Then, permutations associated with nodes are computed simultaneously by solving a permutation synchronization problem. For instance, the spectral solution can be used. This has the effect of reshuffling labels of motions in individual pairs so that the same motion has the same label in different pairs. To sum up, the method presented so far starts with different two-frame segmentations and then combines these partial results in order to get a multi-frame segmentation. First, permutation synchronization is performed to fix the permutation ambiguity. Then, robust voting is done in order to handle noise. Observe that this approach is local as each image is segmented based on its neighbors only. Local solution previously appeared in the literature in the case of rotations and rigid motions. Now I will show some experimental results on motion segmentation datasets, where performance is measured in terms of misclassification error, that is, the percentage of misclassified points. First, let us consider the popular Hopkins dataset, which provides noise-free trajectories across multiple images. Both the spectral solution called Sync and the local solution called Mode achieve good performances in terms of misclassification error. The fact that they are not the best is not surprising, since they are making more difficult assumptions, namely pairwise matches instead of multi-view trajectories. Let us consider another dataset consisting of moving objects in an indoor environment, where shift matches were computed in order to provide two-frame correspondences. Two methods performing trajectory clustering were also included in the comparison in a combination with a state-of-the-art technique that computes trajectories from pairwise matches. The lowest error is achieved by the local solution on all the sequences, outperforming the competing techniques. The spectral method instead presents a few failure cases. For visualization purposes, I also report some qualitative results on sample images from different outdoor datasets, where different colors encode the membership to different motions. We can appreciate the superior accuracy achieved by the local solution on all the sequences. To sum up, experiments show that methods belonging to a specific category are suboptimal when applied to the task associated to another category. If we restrict to the middle category, that is, motion segmentation with two-frame correspondences, then the local solution is more accurate than the spectral method. Now I will report some concluding remarks on the first part of this talk. The spectral solution presents several advantages. First of all, it is very general, as it can be applied to any group admitting a matrix representation, such as rotations, rigid motions, permutations, and homographies. It can also be applied to sets that do not have the structure of a group, such as the case of binary matrices. Moreover, it involves a variety of applications in computer vision, including structure from motion, registration, matching, mosaicing, and motion segmentation. Finally, it entails a simple implementation, namely a spectral decomposition and a projection step. The main drawback is that the spectral method is an approximate solution that does not enforce geometric constraints, hence it can be suboptimal. Concerning the local solution, it is more accurate than the spectral solution on motion segmentation datasets. Moreover, the framework is modular, so it can be easily generalized to more practical scenarios. For instance, methods working with an unknown number of objects are available both for fundamental matrix fitting and permutation synchronization. The main drawback is that this algorithm is specific for motion segmentation, so it is hardly generalizable to other computer vision problems. Now I will move to the second part of my talk, that concerns cycle consistency and localization. I will start with a brief introduction to localization problems and translation synchronization. The task of translation synchronization is to recover the position of n nodes in this space, starting from pairwise differences, as stated by the consistency constraint. Observe that the solution is defined up to a global translation. The unknown node locations can be recovered as the solution of a linear system of equations, which can be expressed in a compact matrix form thanks to the usage of the Kronecker product and the incidence matrix. Here, X denotes the block matrix with all the unknowns in columns, and Z denotes the block matrix with all the measures in columns. Audience not familiar with Kronecker product and incidence matrix can find an appendix on these topics at the end of the PDF of this talk. Observe that if the graph is connected, then the rank of the incidence matrix is n-1. Hence, the rank of the Kronecker product between the incidence matrix and the identity is dn-d, where the rank deficiency corresponds to the translation ambiguity. Translation synchronization is an instance of the more general localization problem. The goal of localization is to compute the position of n nodes in this space given measures on the edges, which can be either directions or distances or differences. In particular, we are interested here in direction-based localization, which is also known as bearing-based localization. Observe that this is not a synchronization problem according to the definition of synchronization given at the beginning of this talk. Now I will give more details about bearing-based localization and the related theory of parallel rigidity. The goal is to recover the position of n nodes in this space, where pairs of nodes can measure the direction of the line joining their locations, as shown in the formula. This problem can be modeled as a graph, where nodes correspond to the unknowns and edges correspond to the pairwise directions. Observe that the solution is defined up to translation and scale. Now I will explain an interesting formulation of bearing-based localization. Let us rewrite the consistency constraint of translation synchronization in terms of directions, which are known, and magnitudes, which are unknown. A compact matrix form can be obtained thanks to the usage of the Catril-Rao product, as shown in the formula. Let us consider a cycle matrix C and multiply both sides by the Kronecker product between C and the identity. Since the incidence matrix lies in the null space of the cycle matrix, the left side vanishes. Audience not familiar with Catril-Rao product and the cycle matrix can find an appendix on these topics at the end of the PDF of this talk. Thus, we get that the Catril-Rao product between C and U times alpha should be 0, where C is the cycle matrix, U is the matrix containing all the directions in columns, and alpha is the vector containing all the scales. Now I will explain the meaning of this equation. First, a cycle basis is computed, that is, a minimal set of cycles such that each cycle in the graph can be expressed as linear combination of these cycles. Each cycle basis is associated with a cycle matrix, where each row corresponds to a cycle and each column to an edge. Positive and negative entries correspond to edges traversed in forward or backward direction. Then, a homogeneous linear system is formed where each equation corresponds to a cycle. In this way, we are imposing cycle consistency, that is, the sum of pairwise differences along any cycle in a basis is zero. Now I will speak about under which conditions bearing-based localization is well posed. Requiring that the underlying graph is connected is not sufficient for unique localizability, but the graph is required to be parallel rigid. Parallel rigid means that all the configuration with parallel edges differ by translation and scale, as happens for the left figure. In the right figure, instead, the graph is flexible since there exist non-trivial transformations that keep edges parallel. If we assume generic configurations, then parallel rigidity depends only on the graph and dimension D. It can be shown that node locations can be uniquely determined from pairwise directions if and only if edge lengths can be uniquely recovered from pairwise directions. In other words, checking parallel rigidity is equivalent to check the rank of the cut-row product between the cycle matrix and the matrix with the directions. This result provides an intuitive way to look at rigidity since the problem is formulated in terms of cycles in the graph. For instance, thanks to this result, it can be shown that a single cycle is rigid in 3 space if and only if its length is 3 or 4, whereas longer cycles are flexible, as shown in the figure. Moreover, it can be shown that a rigid graph does not contain neither articulation points nor bridges. In other words, a rigid graph remains connected after removing any node or edge. This provides a simple necessary condition for parallel rigidity. For instance, it can be checked that the graphs in the figure are flexible. Observe that the union of rigid graphs with at least one edge in common is also rigid. Using this information and previous results, it is possible to classify all the graphs in the figure in either rigid or flexible in tree space. Now I will explain how to apply the rigidity theory to the structure from motion problem. The task of structure from motion is to recover both camera positions, orientations, and the coordinates of 3D points, starting from multiple images of static scene. It is well known that we can compute the directions of pairwise translations from epipolar geometry, but the magnitudes are unknown. In other words, estimating camera positions is an instance of bearing-based localization in tree space. Structure from motion can be represented as a viewing graph, where vertices correspond to cameras and edges correspond to view geometries. If the viewing graph is parallel rigid, then estimating camera positions is a well-posed problem. If the graph is flexible, then the largest rigid component has to be extracted, which represents the largest subgraph where the problem is well posed. The rigidity theory can be applied to popular datasets used in structure from motion. It turns out that only the Notre Dame dataset corresponds to a rigid graph, whereas all of the others are flexible, as they contain both bridges and articulation points. In order to give a better intuition, I report here a simplified representation of the graphs corresponding to two datasets. The gray circle represents the largest rigid component. Edges not belonging to the largest rigid component are drawn in blue. Nodes which are endpoints of such edges are drawn in red if they belong to the largest rigid component, or green if they do not belong to the largest rigid component. All of the remaining nodes and edges are not reported. Now I will report some concluding remarks on the second part of this talk, that is, localization and cycle consistency. I showed that translation synchronization and bearing-based localization are localization problems with different input measures, namely pairwise differences versus directions. Accordingly, they require different assumptions. Translation synchronization is well posed with a connected graph, whereas bearing-based localization is well posed with a parallel rigid graph. Bearing-based localizability can be formulated in terms of cycle consistency. This gives an intuitive way to look at rigidity, since the problem is expressed in terms of cycles. Structure from motion is an instance of bearing-based localization in tree space. Most popular datasets are not rigid, as they contain bridges and articulation points. Finally, observe that parallel rigidity assumes a calibrated setting within structure from motion. If cameras are uncalibrated, then a more general notion of solvability is needed. You can find the slides of this talk and more material about synchronization and cycle consistency on the website of our tutorial. Thank you.